I have a short presentation to give on the work I've been doing on error correcting codes. I've got some slides now, so I'll go ahead and do a screen share, but 1 second. I gotta get the machine joined. Kent, did you already give an update?
Yeah, more or less. I guess it's mostly just been there's nothing on the research front, so to speak.
Okay.
Just we basically went through how the proof of stake contract will work in terms of bonding and the flow of rev transfers.
Cool, I get that. How are things going with the recent bug that you put some logging in for?
So that's still in progress.
Okay, all right. Well, let me know if I can help in any way.
Sounds good. Yeah. Whenever Tomasz gets to so apparently the issue is that I mean, it's pretty trivial to launch two networks, but
Yeah.
the issue is all the I forgot the terms. I think so. The pubnet is the one that I think is currently running, and then there's devnet, and that's how we're differentiating the two testnet names.
Got it.
The pubnet nodes know the devnet nodes, so whenever you boot up both, like one tries to connect to the other, and
Got it.
It's I mean it shouldn't be that hard to fix, but I think Tomasz is bogged down with other stuff too. I'm not quite sure, but
okay. All right.
That should come over the next couple of days.
All right. I'll also, talk to him and see what's going on.
Yeah, another thing is, like, if it becomes really urgent, then we could just think about setting up more, like what Dom did with a private network. We could just have I guess like a third test net.
Yeah, I think it's totally fine to have a private network that just the devs are pounding away on, right? So, what are error correcting codes? So, in order to transmit a message made from words over an alphabet sigma over a lossy channel, where you can potentially lose information or duplicate information or reorder information. What you do is effectively introduce redundancy and other kinds of perturbations to the information you're sending. And here's a really simple example that I mentioned last time. So if for every bit that you send 3 bits, then then it's effectively it becomes a kind of voting scheme, right? Where if you see three zeros, then that's clearly a 0. If you see 3 ones, that's clearly a 1. If you see 2 zeros, that's a 0 with some percentage chance of being wrong. And if you see 2 ones, that's a 1 with some percentage chance of being wrong. So that's a simple scheme. Now, the interesting thing is that what we've done is we've gone from sending a single bit to sending words in inverted commas here, because they're not words in the usual sense of computer science. But what that means is that there's an encoder turn 1 bit into 3 bits, and a decoder turn 3 bits back into 1 bit. And that's dual to a variation of the protocol that would send the individual bit 3 times, right? And the other end of it, which would have 3 receives and know what to do with them, right? So those are 2 different ways you can do it. You could send all 3 bits at once, or you could send it 3 times. And there are some examples of those kinds of protocol extensions that deal with loss and noise, and I'll get to those in a minute. But just the general idea is that there's a duality between encoder-decoder pairs and elaborations of the communication dance between the participants in a protocol. So some examples where instead of sending more structured information, we're changing the protocol is the alternating bit protocol. So those of you who grew up in the 80s and 90s may have been exposed to Milner's CCS analysis of alternating bit. And then there's the grown-up version of alternating bit, which is high watermark, and that's the heart of TCP. So those are 2 examples where it's not that you're sending the more structured data, but you're extending the communication events in the protocol to protect against noise. And there's just this duality between the 2. And that duality is important because what it does is it represents, it allows us to treat an error correcting code as a bound on or governing the extra communication events in the protocol. So we can see sending certain structured information as a way to say, and this is all you can do in terms of the extra communication events in the protocol. So that's the key idea. It becomes a constraint on how much communication you can do. And that constraint is our synchronization constraint. So how do we formalize this in our setting? So these are all some pretty straightforward intuitions that come from literally decades and decades of work on communications protocols. So in the row calculus, direct communication is given by the COM rule. So you've got a process that's waiting on X for some data that we're going to bind to the variable Y when we run P, and we have some process running in parallel that's sending the data Q on that channel X. And when they meet up, then we start running P with the code of Q substituted in for Y in P. So that's the basic COM rule. And now it turns out that we can treat encoding and decoding or this extra communication dance as a context that we wrap around the data. So I've just been suggestive here. I haven't really elaborated, but you can imagine that an encoder for Q would send 3 copies of Q. Really, you want to do this at the substitution point, but I'm just trying to be compact here and express the ideas. And notice that there's a duality between sending 3 copies of Q and sending Q 3 times. So those 2 pairs are easily seen to be dual in some sense. gives you some suggestions as to how this all gets worked out in the math. And the other point is that this approach is compositional. So suppose you have a synchronization constraint K1 and a synchronization constraint K2, then you can whack them together in this way. And that gives you a nice crisp way of talking about the changing the communication protocol. But the important thing is that changing the synchronization constraints on the communication protocol. But the important thing is that you know whatever you do, it's for the lifetime of the protocol in this approach, right? That K is fixed for all COM events for the entire lifetime of the protocol. And the question is, can we do better? Can we change the synchronization constraints during the execution of the protocol so it can be dynamic? And yes, we can. The answer is yes. So I'm not sure why this is like this, but can people see that?
Yes, it's good.
So this is a variation. Oh shoot, I forgot to clean this up. It's missing it's missing a rule. 1 second here. There we go. Let me just grab this one. Okay, there we go. So this is a variation on the road calculus that I've called the space calculus, because it allows us to model a notion of location. So names become locations. For those people who understand the idea of the zipper provides a generic notion of location in a data structure. And it's done so in terms of pairs. One is a context, and one is a term. So a pair, which is context term, give you a notion of location. And here what we're saying is that names are locations inside a term. And so the overall structure of the calculus is very similar to the row calculus. You've got your usual suspects of the stop process, for comprehensions, output, parallel composition, and deref. And then there are two new process constructors. Not surprisingly, since names come in pairs, there's one that has to do with context and another that has to do with terms, which are encoded as names. So the core idea, the key intuition here is that you need a catalyst in order for the COM to run. So you don't get to run a COM unless this catalyst is present. So unlike the ordinary COM here, if we were to just eliminate this for a minute, this is your ordinary COM, and then this is saying that you need this catalyst present in order to actually run the ordinary COM. And the flip side is this thing, which is if you have a content, and the reason you need this is because you can no longer substitute a Q directly, because a Q is not all you need for a name. You also need a context. So here, where we normally would do the code of Q, is not, first of all, it's not a well-formed expression. You need a context. And second of all, you need the context in order to form the name. So you get that context from the catalyst. Right? You grab that context and you substitute it in for Y. And the other piece is you can have competition. So at a point where you're doing a deref, you could snag this deref, take it out of action, and pull the Q into a location X and put the context back into its catalyst form. So this calculus is a little different than the row calculus because there's always some competition. There's always potentially always some additional competition for the catalyst or for communication in terms of deref. So let me just quickly.
Can I quickly ask what the rules for taking a catalyst are? Like, does it have to be in par with the reduction that's about to happen, or?
Yeah, that's what this rule says. Has to be in par.
Okay, thanks.
Yeah, and then the other piece of the puzzle is you have to update your substitution rule so that when you're doing a substitution of this form, that's when you put the Q into the K. So when you're substituting into a deref, that's when you wrapper the Q in the K. And so that gives you a nice kind of variation of the row calculus that allows you to program your synchronization constraints. And just as an example of a calculation, here's a calculation. So the simplest name of all names in that calculus is the one where you have the empty context and the stop process. So I'm going to form a simple row for comprehension where we're listening on this name here for some name, and we don't really care because this is a bound name. And then whatever we get, we're going to start running. When we run that in parallel with sending P on this name here, the simplest name possible in this calculus. And we have this running in parallel with the com K prime catalyst. So this will evolve in one step to applying the substitution at K prime P. So that's the K from the common rule that we had. And we're going to put it together with P, which is the data that's being sent. And we're going to substitute that thing for KQ at KQ in this expression. Now remember, when we have a deref, we go ahead and apply the K to the P. So that's what we've got here. So P moved from being located at this name to being inside this context. Now suppose that K prime is also of this form up here, right? So so P gets substituted in right here, right? And then we'll run this exact thing through, and then what will happen is P will move inside K double prime. right? So this shows that we can have um, P moving through different contexts, which means that P, we can, so in summary, what that does is it allows us to relax or tighten the synchrony constraints on P as is needed for the protocol. So now what I've done is to show that we don't have to have, so I have a nice formalization of what synchronization constraints are, a language for expressing them, and I've shown that we can program those synchronization constraints while the protocol is running. So we don't have to have a fixed set of synchronization constraints. They can sort of be ratcheted up or relaxed as we go, and so this gives a nice crisp framework for talking about liveness in the protocol.
Very good. Thank you, Greg.
Well, my pleasure. This is good fun. The thing that's really interesting is that my goals were no wall clock time. So in addition to wanting to be able to have a programmable notion of liveness, sort of so that I didn't have to commit Casper to any one notion of liveness. The other goal was no wall clock time. Because if I have a notion of wall clock time, then that amounts to injecting a bunch of trust into the protocol, because you have to trust your time service, whatever it is, right? You're going to have to trust that. And a time service is a non-trivial thing. Now, there's a secret goal behind that, which is I wanted time to emerge from the protocol. So effectively, a notion of synchrony constraint is a way of recovering wall clock time up to some granularity. So I've shown now that we have a way of introducing synchrony constraints, programmable synchrony constraints. So it's basically programmable wall clock time. And this is and that sort of goes back to why I call this the space calculus. So now I have justification for calling it a space-time calculus. And the idea is to kind of get in a setting like this something that is in analogy with Einstein's field equations. So what we have is a way of locating in contexts and in time. So in other words, we've got a kind of metric where we can put what stand in for matter and energy. So the Einstein field equations, they give you, they say that the stress energy tensor, which describes the distribution of matter and energy within an Einstein a manifold that matches the constraints for Einstein. They just give you the distribution of matter and energy in that manifold. And the metric tells you how far apart things are in that manifold. And the two are recursively related. So if you sprinkle some matter and energy in a manifold that satisfies the Einstein field equations, then what you get is the stress energy tensor causes them to start moving, because it tells you how far apart they are, and how far apart they are changes the stress energy tensor, which then changes how far apart they are, which changes the distribution, which then and around and around and around you go. So it sets up a kind of evolution of the manifold, of the matter and energy inside the manifold, and that's what's going on here. The COM rule is describing that kind of evolution. So you start with some initial conditions, which is some term in this space calculus, and it starts um, and that term describes how far apart the processes are. How far apart processes in that term are, because they'll be located inside. If the process has any names whatsoever, the processes will have the processes inside those names will be located, and their locations will begin to change as the term evolves, and you'll be able to observe a notion of time that arises from the synchrony constraints given by the context. So there's some the time and the space associated with this matter and energy, aka located process terms, is going to change as the term evolves. So the whole calculus is set up to solve two different problems at the same time. One is this idea of using error correcting codes to give us this liveness approach. But the other is to provide a kind of discrete analogy for what is a continuous phenomena in physics. So that's kind of the secret hidden hidden agenda inside this solution. And why I wanted no wall clock time, because as soon as you have wall clock time, then your solutions are not compositional, in addition to having this other issue of trust, and this is clearly compositional. All right, I've taken up way too much time on this, but
That was good. Thank you.
sure.
Awesome. Now, this locality, you're creating a space. So you spoke about I forget what they're called. These other spaces.
Yeah, that's right. The de Sitter spaces are spaces that form the basis of certain solutions to the Einstein field equations.
This is like establishing a locality.
Yeah, a de Sitter space will give you a notion of what's near and far.
So what you're doing, in essence, is you're coming up with a global notion of time within the de Sitter space.
No, this is distinct from the quantum error correcting codes, which give you and what they give you is anti-de Sitter spaces. So it's the dual to de Sitter spaces. So this is not quantum error correcting codes. I haven't taken that step yet, although Mike and I have been having some interesting discussions recently along those lines. For people who are interested, what you want to do is you want to think of I'll just write it down. We're just having fun, right? Nothing serious. This is just research. Okay, so here, let me get rid of this one. So the idea is, what's a fork choice rule? And the thought is, in the quantum setting, the fork choice rule looks like this. I've got I'm asking about I'm asking about one of the eigenstates. So one of the possible branches that my chain could collapse to, right? So here's my branch, and I'll just write it as bra, because that's the standard interpretation of this side. And then on a particular branch, I want to know the value associated with a particular transaction. So I'm looking at an observable, say O, or let's say OBS. Okay, so that's my operator. And then I know the state of the chain so far. So this is my cat, which is the state of the chain. Now that is typically the formulation given in, say, oh gosh, I'm blanking on his name. I mean, it shows up in Heisenberg's formulation, but the Bra-Ket formulation is oh God, why am I blanking on his name? I'll look it up in just a second. But anyway, so this gives you the probability of observing the eigenstate bra.
Paul Dirac.
Well, I'm sorry, Paul Dirac. Thank you. Yes, it is. This is the Dirac formulation of quantum mechanics. So it's the probability of observing a particular value in a particular transaction given the state of the chain. So this is the fork choice rule.
Now, in a deterministic formulation, that would be possibility of observing a value in a particular.
Yeah, something like that. Something like that. It is in state cat. So this is the idea, is that in fact that the chain is the chain is being built out of quantum states rather than out of data structures like we do it today. So this is in connection with the kinds of things that one might do in that case, Jim, where you want error correcting codes on top of quantum protocols. And here, what we're talking about is a consensus protocol. So you'd like, so Prakash Penagadin observed that there are ways to do leader election in quantum protocols, and more generally, there's a nice approach to doing distributed consensus in a quantum world. There are a bunch of papers on this at this point, some pretty influential papers. And if you want to layer some error correcting on top of those quantum consensus protocols, which is a natural thing to do, those error correcting codes, at least in certain quantum protocols, correspond to anti-de Sitter space, to come full circle to your question. But that's over in the quantum world. Here, I'm just talking about a discrete data structure, right? That operates in an analogy to the Einstein field equation. So so the Einstein field equations are providing a kind of they inform the way we've done the algebra. But we are absolutely headed towards being able to do this in a quantum way. We'll hopefully be talking with Bob Kuka in the next week or two about some ideas in this regard, some research in this regard. Go ahead.
I would suggest that once you have the notion of location, you have a notion of distance, and
Yeah.
You have the notion of independent clocks. And
Yeah, we can recover things like, the light cone, and when things are acausally,
right,
when they're going to be reorderable, and all of that stuff has, precise analogies in this setting.
right, and basically the consensus is eliminating orthogonal clocks, black holes.
Something like that, yeah. At least for a particular group of observers, they all have to come to agreement on a class of events. Yeah, agreed. So, yeah, I'm in agreement with that. Hey, look, my battery's about to die, and I have to run to a power supply. So I'm going to jump off here, and Kent, I'll see you on stand up in just a few minutes.
Sounds good. See you then.
Thanks, Greg. Well, that was awesome as usual.
Yes. Good fun. Ciao.